Alright, so this is the video section for Project 2 with Dr. Ozbay, which is the boundary layer over a flat plate in 2D. So I did do this project by myself, so I'm just going to go through all the parts on my own. I'm not necessarily going to show exactly how I set up everything, like I'm not going to go through and do the entire project. Um, I'm just gonna go through and like show how I did each part, like it says in the instructions here. So starting in Workbench, here I'll just start at the beginning with our geometry. Okay, so pretty simple. It's just a rectangle. There were some specifications in here. Yep, a plate length of 100 centimeters. This is 100 centimeters, and yeah, I think it is 0.15 meters tall. I don't believe the height actually matters like all that much. I know you can't make it too small because um, that'll cause problems if you don't give like the boundary layer enough room. But like you can make it like I don't know 0.5 meters, and I don't really think it'll have that much of an effect since we're really only working with the bottom. Um, So yeah, simply just make a rectangle. I sized it using the dimension tools. And then I also actually that's in the next step. So yeah, that's our geometry. Pretty simple. Um, and then let's open up our mesh. Okay, so here's our mesh. Man, it doesn't really matter if I zoom out. But basically, we did the edge spacing. I think it's here somewhere. Yeah, so the edge sizing here, as you can see on the top and bottom, they are the same number of divisions, 150. And we did do a bias. The bias that we selected was this one where it's kind of leading to the right, more dense on the right there. Okay, well, let's not change that. Ideally, it is the top one, I believe, or sorry, the second. Yeah. Yes, it is that one. And what we're looking for is we're looking for a more dense collection over here in the bottom left compared to the right. It's the same thing with the top. And you might actually have to reverse the bias. As you can see, I reversed it here, but on this bottom one I didn't have to. Yeah, so 150 divisions, bias factor of 20. And then for the sides, the bias is the same, except now we did 80 divisions, and then a much higher bias factor of 200. Same thing with the reverse, where this one I reversed, although this side didn't have to. Um, and once again, we're looking for it to be more packed down at the bottom left hand corner there. And then yes, and then I also went and named the selections, inlet, outlet, top, and then plate, which is the plate that we're actually going to be analyzing. So that is really it for the mesh. Okay. Uh-oh. Looks like I might have changed something that's probably not good. So whatever, we'll just do edit. All right, so once we're in, there's a handful of things that we have to change and set up, just like the previous project. So let's see, I believe, yes, first we change viscous to laminar. I believe typically it's, yeah, viscid. So yeah, make sure you change that to laminar. Materials, our fluid is air, and we make sure to change it to these values that were given into, or in the actual assignment details. So 1.2 for the density, 1.8 e to the negative 5 for our viscosity, so includes that. Now for our cell zone conditions, we just make sure that, yep, the material is set to air. Boundary conditions, so our inlet, of course, is a velocity inlet. Outlet's going to be a pressure outlet, as well as the top. Now, originally I did have the top set to symmetry, but it was causing some problems. Basically, my free stream velocity was not was kind of a weird overshoot. So I did adjust it, and I believe it has to be a pressure outlet anyway, since we're only analyzing, the bottom. Um, it should be open. So then our wall, of course, which is the plate, which is our bottom wall. And this is just stationary, non-moving. Typical. It's frames. Oh yes, our reference values. This is extremely important to change. So we'll make sure to change these. So area, just set it to 1, straight up 1. Our density is 1.2, just like in the assignment details. Depth of 1, length of 1. And some of these values are already input for you, and you just leave them. I believe the only thing you really have to change is the density, maybe the length, the viscosity, velocity, and that's really it. Everything else should already be how it's supposed to. So that's really that. Is there anything else? Coupled scheme. Pressure second order, momentum second order upwind. I believe that's it. Initialization, it doesn't matter if you do hybrid or standard. I just did hybrid. So I'll just initialize and calculate, and we'll see what this gives me. And this is also how you get your values for part D. Well, I guess I'll just do that later. I'm not gonna jump ahead too far. But okay, so we ran that. We can close this now. So now we can open up our solution. I'm just gonna update all this since we just reran it. Okay. Finally. Okay, it's taking quite a long time. I think it's almost done. Show one message. Okay. There you go, finally. So now that we ran it, I guess we could just jump straight to results. Okay, so starting out, just started out with the pressure contours, so I'll show you this. So, yep, the location is set to symmetry 1. To be completely honest, I don't really know why, because if you set it to plate, it does not work. Anything else doesn't work. Symmetry 1, though. I think symmetry 2 also works. No, it does not. Never mind. Scratch that. Variable. Okay, well, it's supposed to be pressure. Set that to pressure. Number of contours 500. It doesn't exactly matter. Like, I mean, obviously you don't want to do a number of contours that is too low, because your contour will be super choppy. But it doesn't have to be like, super high. 500 is kind of a good sweet spot I found. So I'm just going to zoom in on this a little bit so you can get a better look of what it should look like. See, it's very, very small. Okay. And then for our velocity contours, it is basically the same thing. Here, I'll open this up. Oh yes, so our range, I did change the range to be from 0 to 2 because I did have that slight overshoot that I mentioned earlier, which is why I changed it to the pressure outlet. But even aside from that, I did change the range to be from 0 to 2 since our free stream velocity should be a maximum of 2. Of course, this is not going to be perfect, but so yeah, it's basically the same thing. Not really anything to show you here. So yeah, that is our velocity contours. Oh, also for the legend, I did make a few adjustments to this just so it's a little easier to read, because I know the default legend is kind of crappy. And then lastly, our velocity vectors. Ooh, these things are teeny weeny. I'll make them a little bigger. I don't know why they're so small. Oh, probably because I reran. I'll do something like that maybe. There you go, that's a little better. So you can get a decent look at the vectors here. It's basically about, what we expect. As soon enough it reaches its free stream velocity and, kind of evens out. Okay, I'm trying to use this. Okay, anyways, so the options for the velocity vectors, symmetry, variable velocity, sampling. You don't actually have to vertex because sometimes it makes it look it makes it a little hard to read, but I did opt for vertex. Because you can always adjust the symbol size and stuff, and that does typically help. Now, that is part A, I believe. Nope. Tours around the flat plate. Yes. Okay. Now, so for part B, made 2 lines. Pretty simple. You just go insert location line. I'll just show you the locations real quick. 0.35, 0.35, 0.15. This one's 0.75. Remember, 0.15 is our height, so of course we're gonna go there. Then we make our actual XY plot. This is just like, or our velocity profile plot, which is just like the first project in terms of setup. So velocity profiles, data series, you set them to the same points. I believe last time it was like 0.75 and 0.5, and so this time it's basically the same thing. Velocity U, that's what we're looking for in the X direction. Our Y is set to Y. I did change the range a little bit because it does show all that excess, which of course is redundant. We do not need to see that on our graph. So yeah, that's really it. But it'll, look something like this. Now, you should export your data and so that you can actually analyze it in Excel. And that is what I did here. It's one of these. Yes, this one for part B. So as you can see, exported the velocity values from 0.35 and 0.75. And then in this Excel, here's just all the reference values from the assignment, which I also have another one for the which I'll go over in part C. But very simply, I just rebuilt the graph in here to show the Blasius theory or the Blasius solution like in the same graph instead of having to have two separate ones. I think this makes it a little easier to to see. But anyways, you can see the shape is extremely similar, very very close, and we can also pull our boundary layer thickness from this. So basically, the boundary layer thickness is where our free stream velocity reaches, or the height where the free stream velocity is like 99%. So that would be like somewhere around here, and like on here. I do have the values in my report, so let's see. Yes, right here. Yes, so at 0.35, our delta was, or our boundary layer thickness was 6.95, 0.75 was 10.4, and then we can compare that to our Blasius theory, Blasius solution, and that tells us that our real, or fluent delta, I guess not real, was actually 14% thinner at our 0.35 and then 12% thinner. So overall, it was, over 10% thinner than our Blasius solution. Okay, so then for part, see, let me just get a little refresher on it. Yes, so this was basically the same thing. I, however, did not plot it in Fluent. I'm sure you could, and I'm sure it would look extremely similar. I might as well just go ahead and actually, I think I did try to do it, and it was just not really working. That's why I opted out of it. But anyways, you can go up here, File, Export, type generic. Our location will be the plate, that we're working with, like I mentioned earlier. And then the variable will be wall shear X. This is what we're looking for. And from this wall shear X value, and it'll also give you the corresponding X, Y, and Z values, you can find your skin friction coefficient. And then using the given values, you can find your Reynolds number and all the other stuff that you need to find your Blasius solutions to compare. So yeah, once you save this to wherever, I'm not going to since I already did, which is in here somewhere. Actually, I think I might already have it open. Yes, here it is. So this is basically what it was originally. These columns, this is what we were given. Just ignore this. These were all 0, so let's just ignore that. Oh, that's not proper. Our Reynolds number seems to be incorrect. That is quite interesting. Oh, okay. My computer was just bugging out, I suppose. All right. Well, for part C, we export our our data. This is, and like I said, it'll be like these 4 columns whenever you export it. I just threw in our reference values to make it easy. First thing that we do is calculate calculate our skin friction coefficient. I was not able to find a way to export it from Fluent. I don't know if I was doing it wrong. Or what, but you can calculate it yourself, which I'll explain how I did now. So you calculate your dynamic pressure, which is simply 1/2 rho u squared, or v squared, whatever you want to call it. So you can see that in here, or sorry, wrong one. Okay. Let's not do that. Yeah, so 1/2 rho v squared. And then our skin friction value, or coefficient, sorry, will be our wall shear value divided by the dynamic pressure at each x point. So as you can see, they all line up. So that's how you calculate that. Then for Blasius, you basically just use all these equations that were given to us to find our Blasius solutions. So the wall shear, I believe if I click on this, you can see the equation. Yes, so you see 0.332 times mu to the 0.5 times rho to the 0.5 times velocity to the 1.5, sorry, divided by our x value to the 0.5. Then you just copy it all down. You do the same exact thing for the skin friction coefficient, and then the same thing for your Reynolds number in the x. Okay. Oh, and the Reynolds number in the x is our typical Reynolds number, which we calculate from all of this, of course. And it is, yes, so it is our rho v, and then our x value divided by our mu, and then we just do that for every single row. Okay, just do that again. Okay, I don't want to mess up all my data here. Okay, then I just moved all of the data that I needed, so x, my wall shear, Blasius wall shear, skin friction coefficient, Blasius skin friction coefficient, so that I can make the two graphs for it, which also shows our Blasius solution on the same graph, so it's easy to compare, just like the last velocity profile one. And then I believe in here we have, I do have the actual values. So yeah, now just for part D, the drag coefficient. So the drag coefficient found from Blasius theory, which I have in here. And this one's right. There you go, 3.64. Actually, the actual value. Oh, never mind. 3.64. So like point what? 0.00364, something like that. Yes, and then if we compare that to our CD, which was found in Fluent. Oh, yes, that's what I was going to do. Let me show you how to find that in Fluent. So let me leave here. We'll go back into Workbench, open up Solution. Okay, cool. So I'm just going to go here to Results, Reports, Forces, and we're going to run it in this direction, so 100. We're going to select our plate, click Print, Close, and as you can see, this is our drag coefficient given from Fluent. And then comparing that to our Blasius solution, we have an error of plus 16.1%. So it was, slightly higher, slightly 16% higher. Anyways, that is part D. So I think that is everything. Yeah, so yep, I believe that is also. My name is Hayden Kaliji. Here it is at the top. This is project number 2 for Dr. Ozbay. 5634076 is my UCF ID number. Yeah, and thank you.